All right, so they sent out a message about the exam. Everything is going sort of normal tomorrow for us. We are on virtual campus, but I think that we'll be able to meet if you want to come in and take the exam here. I'm pretty sure that we'll be able to do that. I'll send you final confirmation for that later. Okay, I'll send you an email. So if you want to come in and take it in this classroom, pretty sure that'll be okay, but I'll let you know later today. But otherwise, you'll take the exam on Respondus. Please make sure that your computer is working with Respondus. I don't think we've had any issues. If you've had issues, just let me know. We can sort it out. But I'll send you out my cell number. You can call me, call on text, on email, or call me on the phone, and then we'll work through whatever the problem is. Okay? All right. The exam is on Chapter 7 and 8. Chapter 7 includes these topics. We'll have just sort of angles, kinematics, and centripetal forces. We can look at each of these and look at sort of examples of them. And then in Chapter 8, we have torques, moment of inertia, energy, rotational energy, and translational will come in there too. And then also angular momentum. And in each of those, when I go through and make out the test, I try to have a balance of calculation type problems and then also the conceptual problems. Okay? And any of those topics in particular that you want to look at today, or you have questions about particular exam questions that you want to look at? Yeah, Cameron?
All 18 examples.
Okay, which number? Which one?
Number 4.
Number 4. Okay, so you will have a question regarding centripetal forces. There are usually several different types of these. This is one of those types where your centripetal force is the static frictional force. Some frictional force is acting between the object that's traveling within a circular path. And then there are 2 others. I can describe those to you as well. But let me go to this one first. So I have a car that's going around a curve, and the force that is the centripetal force is the static frictional force. That's the frictional force between the tires and the road. Remember, centripetal force is not a new force, that you're just using that term centripetal force to describe a force or forces that already exist. And in this case, the centripetal force that causes the motion in a circular path that's center seeking is the static frictional force. And so I know that static friction is mu Fn, and that's going to be mu times m times g. That's from Chapter 4. And I know that that's also going to be my centripetal force. So mu mg is equal to m times v squared divided by r. And I'm looking for the maximum safe speed, so that means that I'm looking for v. Notice my masses cancel out, and then I can solve this for v. It's going to be the square root of mu times g times r, which is going to be the square root of 0.7 times 10 times 50. Square root of 7 times 50, square root of 350. It should be 19. Okay? Now there are 2 other types of problems that you'll probably encounter. You might see a couple of these. One is a problem, we've done this in some of the classes, I think, where you have a rope that you're swinging over your head in a horizontal circle. And when you're doing that, usually the way this question goes is that, I have this rope. Say I have a person, like a lasso kind of thing, and they're swinging this rope over their head. And then I have, let's see, this doesn't really work. I have a ball or something on that rope. Y'all get the picture? Like a lasso I'm swinging over my head. And I want to know what velocity or what is the tension in the rope. And the tension in the rope would be equal to m times v squared over r. So that's another type of problem. We can look and see in some of the other tests and find an example of that. The third type of problem, which is really a bit more complicated, but it's still the same idea, is where I have a situation, well, it could be the rope in a vertical path. So when I have a rope that's being swung in a vertical path, and in this case, if I have a ball on a string, so now instead of doing it over my head, now I'm doing it like this. In some of your classes, we did this like the Ferris wheel problem. It's the same idea. And you have an example in your chapter at the end of chapter homework for a Ferris wheel. But in this case, the normal force isn't just the centripetal force isn't a single force. The centripetal force is actually a sum of two forces. And so the centripetal force is going to be the tension, Ft, and the weight, Fw. So that is our centripetal force, where the sum of these forces is equal to mv squared over r. Or, negative Ft minus Fw equals mv squared over r. We have varieties. Those are sort of the three types of problems that you see regarding centripetal forces. Other things about centripetal forces that you need to know is that centripetal forces are always center-seeking. That's what centripetal means, that they're always towards the center of the path of the circle. They're the force that cause an object to move within a circular path. Also, when you're calculating centripetal forces, we use this equation, mv squared over r, but there is another equation that you can use. Because v is equal to omega r, if Fc is mv squared over r, I can substitute this in for v, and I get a different expression, which is m omega squared r. And so if you're given omega instead of v kind of problem, if you're given the angular velocity instead of the linear velocity, that equation you can skip a step if you know that equation. But otherwise, if you're given omega, you can always find v by this relationship. Okay? So that was a long answer to a single question. Also in that chapter 7 are kinematics and angles. Any other questions about chapter 7 that are particular questions or particular problems on exams? All right. Well, of these topics, do you feel that there are some that you're weaker at than others? All right, why don't we just go to an exam and we'll sort of scroll through it, and you let me know as we sort of go through them which ones you want to work on. Let's go to exam. Let's go to exam 3 of fall 15. So this is exam 3, fall 15. I think. Yeah. So as you're going through some of the old exams, usually chapter 7 is at the end of exam 3 and chapter 8 is at the beginning of exam 4. That's usually, you can always tell, like for example, I can identify where I go from chapter 6, which is all about momentum, into chapter 7. And in this case, it's between 19 and 20. So for example, on this fall 15 exam, I'd pick up with problem number 20. You'll see some questions where you have to convert units. In fact, there are several questions on the 25 questions on the test that require you to convert units. So be on the lookout for those. Some of those are explicit questions like this. And then others are questions where I give you units or I give you angles in one unit, and then I ask for the answers in another unit. I try to be really clear. I try to bold it, explicitly state that I want them in that unit, but just read your problems carefully, and if I'm asking for units in a different unit than what I give you, just sort of make a note, sort of, I don't know, pinch yourself or whatever to help you to remember at the end that you're going to need to convert your units. Just be aware that is going to happen tomorrow, and I don't want you to miss a problem just because you don't convert the units. Okay, so conversion of units. You need to know your unit conversion factors. 1 revolution, 2 pi radians, 360 degrees. That comes up 20, 21. 21 helps if you know the your unit circle. 0, pi over 2, pi, 3 pi over 2, 2 pi. Although in this case, you're going from 3 a.m. or from midnight to 3 a.m. So you have a displacement of negative pi over 2 radians. Number 22 there, that's a centripetal force problem. You want to look at 22? Let's think of 22. I want to, we'll do 22, and then I want to do something additional in 22. And number 23 is another centripetal force problem. But let's look at 22. I have a Ferris wheel. The radius is 12 meters. And I want to know what is the centripetal acceleration when the angular speed is 0.5 radians per second. This is actually not a terribly difficult problem because it's really just sort of knowing the equation. My centripetal acceleration is v squared over r, but that's also equal to omega squared r. So omega is 0.5 squared times the radius, which is 12 meters, and so that's a quarter of 12, or 3 meters per second squared. So A is the right answer there. Now, let's imagine that I have this Ferris wheel, and let's say that the person sitting in the seat has a mass equal to 100 kilograms. And I want to know if they are at the top of this Ferris wheel, what is the normal force that acts on that person. So I have a person that sits here. There are two forces acting on them. There's the weight, and then there's the normal force, Fn, Fw. Now, if this thing wasn't spinning, the normal force would equal to the weight. So if this wasn't spinning, the normal force would be 1,000 kilograms. Is the normal force going to be more than 1,000 or less than 1,000 if it is spinning? It is spinning. So is it more or less than 1,000? It's going to be less. Let's try to use it. Huh? Yeah, good. It's less. It's a lot like the elevator problem that we did. When the elevator would go up, your normal force would be greater. When it went down, it would be less. And so this is a lot like that. The key to this problem is recognizing that the acceleration, the centripetal acceleration, is down. So AR is in the negative direction, or AC rather, I'm sorry. AC is in the negative direction. So really, I want to give that a negative value, negative 3 meters per second squared. And then it's applying Newton's second law, just like we did in chapter 4. Now the sum of the forces equals m times a. The sum of the forces is Fn minus Fw equals the mass times the acceleration. So my normal force is equal to the weight. That's 1,000 newtons. I just did 100 times 10. Right, that's the normal force the person would feel if there was no spinning motion at all, plus the mass, which is 100 kilograms, times the acceleration, which is negative 3 meters per second squared. And so that's going to be 700 newtons. So this person at the top of the Ferris wheel will sort of feel like they're coming up out of their seat just a little bit, whereas at the bottom of the Ferris wheel, when the acceleration is positive, when this number is not negative 3, but it's positive 3, when they're at the bottom, it sort of feels like they're pushed down into their seat. They actually feel heavier than they are because the normal force is bigger. Okay? That's one of the 3 types of centripetal force problems. There are only a couple of centripetal force problems, but let's look at some of the other stuff. Or questions about this? Not scaring you, am I? We're okay? Okay, all right, let's look at the rest of this. Ooh, how do I get rid of this? There we go. You're going to have a kinematics problem, a lot like this. It might be a simple kinematics problem, just a single step, or it could require a couple of steps where you first have to find the acceleration and the time before you have to find something else. We worked through those. It looks like this is a relatively easy one. I'm just looking for the angular displacement. Yeah, I'm looking for theta. That's omega naught t plus 1/2 alpha t squared. I'm looking for the angular displacement. I know omega naught, which is 0.5, that's its initial angular speed, 0.5 times t, which is 7, plus 1/2 of 0.04 times t squared, which is 7 squared. And then you would find the angular displacement. But some of these problems are more complicated just because you don't have all of the values. We'll look for those along the way, and we can try them out. All right, you'll have some conceptual questions about all of these. Like, for example, this one. If alpha is equal to 0, that's the angular acceleration, then what does that say about, in this case, the linear velocity? Do you know what the answer is here, by the way? If the angular acceleration is 0, which of these statements is true? The linear velocity is the same as the angular velocity? Not true. The linear velocity does not change. Is that true? Right. It does not. The linear velocity, in fact, does change because the direction is always changing. Oh, and so that's C. That's what C is saying. That the direction of the linear velocity is constantly changing. So C is the right answer. All right, you'll have some like this too, where you have to, if I give you an angle theta, or if I give you a certain time, I ask you for the relationship between theta and t, or omega and t. Look, you're going to have one of these. It's going to look like a lot like this, where I'll ask you either how does theta relate to t, or how does omega relate to t. And so, for example, in this case, if I double t, I'm going to quadruple theta because I have that quadratic relationship. Whereas here, if I double t, I only double omega because it's a linear relationship. You'll have a question like that. Be prepared for that. I want everybody to get that one right. All right. Nope, that's the end of that one. Let's look at Fall 15, Exam 4. Are there any other questions from Chapter 7 that you want to dwell on a bit? Let's look at Chapter 4. I think Exam 4. This is Fall 15. This first one is a rotational kinetic energy problem. Rotational kinetic energy. There are a couple steps that you have to do here. You have to first find I. This is for a solid sphere. I think that's 2/5 mr squared, if I'm not mistaken. You look on your little table and find the equation for the solid sphere, moment of inertia, and you find the moment of inertia with that. And then to find the rotational kinetic energy is just 1/2 I omega squared. So first you find I, which I said I'm pretty sure is 2/5 mr squared. I could be wrong. You find that. You have M, you have R, so you can find that. And then I want to find the rotational kinetic energy. Oops, excuse me. Ke is equal to 1/2 I omega squared. Now, I don't give you omega here, so you have to find omega. But I know that V is equal to omega times R. And so omega is equal to V divided by R. I have V and I have R, so that's equal to 1 radian per second. And then you can plug that in there. Now, another problem that I could ask you, in fact, I'm surprised I didn't do that here, is not what is the rotational kinetic energy, but what is the total kinetic energy. And if you're finding the total kinetic energy, you're including not only the rotational energy, but also the translational kinetic energy. That's that 1/2 mv squared. That equation is not on your equation sheet, but you know, it looks a lot like this equation, except m where I is and v where omega is. In order to do that, you just take the mass, it's given there, the radius squared, and then you can add up those two energies. They're not vectors, so you can just add them up like numbers. Okie dokie. I would expect a question like that. Well, every question's on the test tomorrow. There are 25 questions, like I said. It's a little bit shorter, but you still get the same amount of time. You have a ranking question like this for moment inertia? Yeah, Logan. Okay, yeah, so you'll definitely have one of these. I will say that when I get this problem, I write here is greatest to smallest. Just make sure that you're clear that on the test that I give you, it's not greatest to smallest, but it's smallest to greatest. I bolded it in the text. I don't know why I did it that way, but I realized afterwards that most of the time I do greatest to smallest on these, but this one's not. It's the opposite. Okay? Can y'all remember that tomorrow? Okay, just read it. I mean, I don't even know that greatest, that the reverse is even an option. So anyway, when you're looking at this, you want to start with the definition of I. I is equal to sum of mr squared. So recognizing that I is greatly impacted, more so impacted, by the distance of the mass from the axis of rotation. That's r. R is the distance of the mass from the axis of rotation. Because it's a quadratic relationship between I and r, I is proportional to r squared. If you increase r, that increases I by so much more. So here, I'm looking for the largest, I'm looking for the situation where the mass is rotating far away from the axis of rotation. And so the one with the biggest axis moment of inertia is going to be about this axis A. And about axis A, this thing rotates like this. And so this bar right here is really far away from that axis of rotation. So IA has the biggest axis of rotation. Then I can go through and I can look at other options to get rid of. Like, for example, I see this IC equals ID, and ask myself, is that even true? Is the moment of inertia about IC equal to this moment of inertia? Are these axes the same? Are these two scenarios identical to one another? And if you look at it closely, I see that about axis C, I have this thing coming out. But about axis D, it looks different. That actually now this bar is coming out in this direction. So IC is not equal to ID, so I can get rid of that. So now really the question comes about, is the moment of inertia about axis D or C the bigger? And that'll help me to pick out the right answer. So which is it? Which has a bigger moment of inertia, about D or C? It is C, you're right. So about axis C, notice that this part doesn't contribute to the moment of inertia at all, but this bar comes out and goes as far away from this axis as possible. Whereas about axis D, this bar doesn't contribute at all, but this part only comes out a little bit, half the distance as the other in the other scenario. So B is the right answer. There are other questions like this that you'll find, but they're all going to be the same, and that you're going to be looking for how is the mass distributed, and I'm looking for the situation where the mass is as far away from the axis of rotation as possible. Okay? Practice those. There are other questions on the test. It will be different than any of those other questions, but those questions will help to give you a feel for them. Those are tough. It helps. I like them because you sort of have to think about how mass is distributed. It gives you good spatial skills to think about those. Okay. You'll have a question like this. Listen, on these, students get troubled or confused about how to treat particles like this 2 kilogram mass. Here I'm looking for a total moment of inertia. There are two components to it. There's the component right here, and then there's this part right here. So there are two parts. One is a bar. I is equal to 1/12 mv squared. That's the equation for the moment of inertia of a bar. And then the other, if there's some extra little particle out here, which is what this is, I is just going to be mr squared. This isn't for a hoop. By the way, that is the equation for a hoop, but this is just for a discrete particle. A particle that doesn't have a shape or size is just a point mass. And that's what that is. It's a point mass. Anytime I have an object like this that's rotating away from the axis of rotation, that's separated from the axis of rotation, that is an object that's not rotating about some internal axis, you can bet that's going to be a discrete particle. So if you ever see some kind of particle that's separate from the axis of rotation, just think mr squared. And you will see that tomorrow, by the way. There is a situation where we have that. You shouldn't be surprised. Okay? Yeah, Michael.
I'm not sure how this might work, but would that imply that that end with the mass, extra mass on it has a different moment of inertia than the other side? Or am I getting you confused?
I don't know, that feels like a philosophical question. That seems a really deep question. But the moment of inertia is always defined around an axis of rotation. So I don't think that you would think about the moment of inertia of a single side. Yeah. No, I don't think so. No. We're really looking at the total moments of inertia of the system. And so it's okay to do it this way, where you add up the moment of inertia of this and of this. Yeah, of course, that's okay. Yeah, the way we're doing it. Don't think about it as two different sides. Okay? I'm pretty sure that's right. Yeah, that is right. That's a good question. Okay? But y'all can do this. Yeah. Tyler.
I had a question for, like it was test number 4 for 2013, number 19.
This was back when I tried giving 5 exams. And I didn't call them exams, I called them quizzes. I thought calling them quizzes would make students feel better about them, but then they didn't really feel any better about them. They still didn't like them. Y'all like exams? No, but they're good. I love exams. All right, which question?
No, 19.
So anytime, or number 19, I was looking at 20. Yeah, so this is a lot like that one we were just looking at. You have a disk, the rotational inertia of the disk is 0.7, and then I add a 2 kilogram weight to it, 0.4 meters, and the moment of inertia for that is going to be 2 times 0.4 squared. And then I want to know what is the total moment of inertia. So it's going to be this is 0.32. So the sum of those, 0.7 and 0.3 is 1.0. That's just like the one with the bar. This becomes important, and you'll see it also tomorrow when we're dealing with angular momentum. Can we go up and look at I'm sorry, specific question about this, or did that answer your question?
No, I was just like, it was the wording that kind of gets threw me off and like setting up the problem. And
Okay.
Just making sure like with problems like that, like whenever you get in like a new rotation, you just pretty much add them at the end.
That's right. So you'll see this in other situations, like on other problems. I remember another problem where you have a merry-go-round, and then you have a kid that comes and jumps on the edge of it. That kid, which is does not rotating about a central axis, is a discrete particle. And so you just treat it as a discrete particle. And it's the same as this, where this is 0.7, this is 0.3 kilogram meters squared, and I just add them up, add the two together. This becomes important if you're looking at a problem like number 20. Number 20 isn't exactly what I mean, but I think you'll get the flavor for it. Number 20 is an angular momentum problem, conservation of angular momentum. And the approach on this will be to say that Li is equal to Lf. Our I initial, omega initial, equals I final, omega final. And so I had this 1 kilogram ball that initially has a moment of inertia of mr squared. That's going to be 1 kilogram times 2 meters squared, so that's 4. And then the length of it gets longer, so 1 kilogram times 4 meters squared are 16. So my moment of inertia increases by a factor of 4. It goes from 4 to 16. That means that my angular velocity has to go down by a factor of 4. So whereas it was 4 revolutions per second, now it has to be 1 revolution per second. Listen, if you don't like what I just did there, that's fine. Just put in the numbers. I have 4 That's my initial moment of inertia times 4 revolutions per second is equal to 16 times omega final. And then I find that omega final is equal to 1 revolution per second. Other problems have two objects that come together where I have like a spinning disc or a flywheel and a spinning bar or a spinning sphere or whatever. And this actually has really practical applications because in a mechanical system, you sometimes have rotating objects that you bring together and then they spin now at a new rate. That's an elastic, a perfectly inelastic collision between rotating objects. Perfectly inelastic because they stick together and then afterwards they move at the same rate. Okay? But they work out practically identical for this problem. Let's look some more at these. This is a good test. Let's take a look. This is let's look at some torque problems. You will have a problem like this where I ask you what is the net torque, and then also I'll ask you other things like what is the angular acceleration, or maybe what is the velocity or displacement after a certain amount of time. On these to find the net torque, this one's relatively easy because I have two forces here that don't provide any torque at all. That both of those forces don't contribute to the torque at all. The 10 Newton, because it's applied at the axis of rotation. And so if I have an object that's rotating, if I apply a force here, it doesn't cause any rotation. The 5 Newton force, if I apply a force here, that doesn't cause any rotation because theta is equal to 180. I have to apply a force here to cause rotation. So neither of those forces cause a rotation. That means that the 20 Newton force at 2 meters from the axis of rotation is the only force that causes a torque. Now further, I could ask you, what is the angular acceleration? In order to do that, you'd have to find first, what is I? For a bar, that's 1/12 mv squared. That's on your equation sheet. So 1/12 of 3 times 4 squared. 3 is the mass, 4 is the length. So that's equal to 4. And then to find alpha, I would say torque divided by I. And so the torque is 40, I is 4, so I would have an alpha of 10 radians per second squared. And then further, I could ask you, what is the angular velocity after 3 seconds, for example? That would be 30 radians per second, omega equals alpha times c. Or some other kinematics question. Or I might ask you, what is the kinetic energy for so much time? Would you have to apply those kinematics equations? Okay? Let's keep looking. You'll have several questions like this. No surprises on the exam tomorrow. All the questions are new, but you will have seen questions that are really similar to them. To clear this out? Here's some more kinematics questions. This is a centripetal force problem. That's like the one where I told you about like a lasso over your head. All right. What else do you want me to work on? I think we hit all the major topics. If I'm not mistaken, let me take a look. Moment of inertia, torques, energy, angular momentum. Yeah, we've hit on all the major topics. So yeah, Krista.
Can we go back to exam 4 and follow the 15?
Of course. Is that this one? Yeah.
Questions.
Okay, so question 7. Notice actually questions 7 and 8 are a series. So I ask you the net torque, and then I ask you after 2 seconds, what is the rod's angular velocity? I know we've mostly been doing bars, right, and finding the net torque, but you should expect some different kinds of shapes. In this case, you follow the same path where I look at each individual force and I ask what is the direction of the torque that it causes. I like to think of a steering wheel, right? Imagine you have a steering wheel, and if I pull down on this side, that's going to cause a counterclockwise. So this force causes a counterclockwise motion, right? It makes it go in this direction. So it has a positive torque. In fact, that torque is going to be 30 newtons times 1 meter. That the distance from here to here is 1 meter. That is the distance to the axis of rotation. Over here, the 10 Newton force causes a motion or rotation in that direction. So it's going to be a negative torque, and it'll be equal to negative 10 times 1, or negative 10 Newton meters. So I add those up. 30 minus 10 is going to be 20. It is positive 20, so that's going to be a counterclockwise torque. Now, in the next part, it asks what is the rod's angular velocity after 2 seconds. To do that, you need to do a couple things. First, find the moment of inertia, mr squared. Mr squared is 2 times 1 meter squared. The mass times the radius squared. Just want to be clear, this is a hoop. This is not a discrete particle. Because of the way that the hoop is laid out, when you actually integrate around the length of the loop, it works out to be the same as for a discrete particle. So it's not a coincidence, but it's not the same either. So my moment of inertia is going to be 2 kilogram meters squared. And then to find alpha, I say alpha is torque over I. That's 10 Newton meters. That's from right here. Divided by 2. That's from right here. That's equal to 5 radians per second squared. And then if you want to know omega, that's going to be alpha times t, or 10 radians per second. That's a good example of the types of problems that you'll see where you have several steps that are embedded in that problem. 3 or 4 questions on torques, so it's not insignificant in your test. Each question is like 2 points, and there are 25 totals for a total of 50 points. Chris, does that answer your question? Yeah. So be prepared to see shapes other than bars, right? Or even you can see a system of discrete particles where you're applying the torque to those. Be prepared, like number 10. I like these ranking questions. It works well in this chapter to do ranking questions. So like number 10, this is where you're ranking the torques. Here I'm ranking the torques from greatest to least. Remember torque is equal to Fr. Sine of theta. So there are a couple ways to make my torques bigger. Here I have a big force and a small r. And here I have a small force and a big R. So these two actually have the same torque. Here I have a small force and a small r. So it's going to be next. And then A is the smallest of all. It's the same as B, except now my force is at an angle. So only a component of this force is actually causing a torque. So the component of that force that causes a torque is smaller than it is in part B. So the ranking here would be D is equal to C, is bigger than B, is bigger than A. Make sure you're good at those ranking questions. There are several like that. Anything else on this test or other tests that you want to look at? Or other just sort of general questions about the exam? Like, I don't know, what are all the answers? No? Okay. Well, then just sort of scroll through. If you come to things like this, where you're starting to deal with fluids, that means that you've gone too far. This is a question about angular momentum, where you have two objects that are coming together. I mentioned that earlier. We did an angular momentum problem, but in this one, I have a bar that's coming together. Let me just work this one. So I have a bar with a moment of inertia of 4, and it's rotating at 3. So 4 times 3. And then it engages with a flywheel, which has a moment of inertia of 8, and it's not rotating at all. And I want to know what is their new speed. They come together. That means you add the moments of inertia, and you calculate the new final speed, just like we did in chapter 6. So that's 12 equals 12 omega. So omega equals 1 revolution per second. Notice I didn't have to convert my units on this. That whatever I put in here, I can get out here. But that's not always true. When you're calculating torque, when you're calculating energy, when you're calculating, I think that's it, the torque and energy. That you have to use SI units for Newton second law of energy. You have to use SI units for angles, radians. All right. Anything else here, y'all? We can wrap it up here. I'll give y'all another few seconds. If you have questions, I'll sort of scroll through here. Hey.
For the seesaw question like that, there was one, and rather than multiplying the mass, like once we multiplied it by 10 to get newtons, instead of multiplying it, if we would divide the total distance by 2, we multiplied it, like let's say it would be 20 times 4. In what case will we multiply by the total distance rather than half, or whatever is divided by?
I think I understand your question.
Yeah, because in one of the exams, it's like the mass times the total distance rather than it's split evenly. And I was just wondering why.
Well, it doesn't have to be split evenly. Like it really is just dependent upon where your axis of rotation is. So like if my axis of rotation is here, then the force will be multiplied by this distance, right?
Or whatever the difference is, I should say.
Yeah, whatever the difference is. So like here, for example, I would have a 20 Newton force that's pulling down on this. And so the torque would be 20 times 2. I don't know of a situation, I don't know that I've ever asked a question where the moment arm is the entire length of the bar. It would have to look like this, where I'd have the axis of rotation at the end, and then some mass over here, and the force would be pulling down. But it's always going to be the force times the distance to the axis of rotation. I'm not sure what that question is. Maybe if you find it, email it to me. Okay. Yeah. All right. You have any other concerns about the logistics of the exam? If you do, if you have personal concerns, send me an email. We can work through them. I understand that the library is giving out laptops, is loaning them out. So if in the past, if you've had issues with your computer not working with Respondus, you might want to go by there today or in the morning. They'll be open in the morning and check out a laptop to use for the exam. Or again, I'm planning to allow students to come in here. I know, like I had a student that just the laptop never worked. We weren't able to get it to work, and so he was able to come in here and take it. If that's you, just please let me know. We can work that out. Yeah. The university's not closed. We're just going virtual. So you're not required to come in, of course. No, nobody's ever, but I'm going to have that option. I think I'm still getting permission from the dean, but I'll send you an email later today. Okay. So the university's not closed. We're just going virtual.